Okay. So sorry about the technical problem here. Anyway, let's start with the Zoom. So we have learned how to generate test patterns for combinational logic circuits. But in a digital circuit, there is more than combinational circuit. We have sequential circuit there. So to consider the testing for those things, there are some design techniques or design for testability techniques. That's the topic for now. So for combinational logics, the D algorithm is a successful algorithm to tackle the testing problem. But testing generation becomes more difficult if circuits are of sequential nature. Because circuit output not only depend on inputs, but also on states of the circuit. States are recorded by the storage elements in the circuit. So we now have to use the Zoom because the screen is not functioning. And for state outputs, they are not only difficult to control, but also can only be observed indirectly. And design for testability refers to those design techniques that can make test generation and test application cost effective. There are two broad categories of design for testability techniques. And the first category is ad hoc design for testability techniques, DFT, design for testability, DFT. So the first ad hoc DFT technique is shown in the slide, is to partition a large circuit into smaller subcircuits. Let's take a break to see to wait for replacement of hardware here. Well, maybe we can continue using this tool. Okay. So let's look at this schematic. Say we have a large circuit. Now we can participate it into two smaller circuits, say C1 and C2. C1 and C2 have normal connection like this. C1, some output is injected to C2, and C2, so some signal is serving as the input of C1. They are interconnected. The way to partition them is to insert multiplexers. Say I insert multiplexer here, insert multiplexer here, and multiplexer is controlled by some test mode signal. Say I have a test mode T1 controlling this multiplexer, and T2 here controlling the second multiplexer. So the normal operation, in the normal operation, T1, T2 will be low. So in the normal operation, the multiplexer has less low input, and we have less normal connection. This zero input, zero sign input for the other multiplexer, and the C1's output goes to some output directory. C2's output goes to the output directory. That's when T1, T2 signals are low. Now say we wanted to test C2 alone. We wanted to test C2. What we do is set T1 high. Set T1 high. Okay. Okay. Let's take a break. Bye. Oh, okay. Now, say we want to test circuit 2, sub-circuit 2. We make T1 high, and we can apply some input through this multiplexer. We can control input through this multiplexer into C2. And this output of C2 goes to some output so that it can be observed. And if we wanted to test C1, we set T2, the test mode signal T2 to be high. Let's go through it. we wanted to now we wanted to test C1. So we set T2 to be high. So we have a input from a signal from primary input that goes into C1. So we can control input. Now let's input to C1. And let's output of C1 can be observed through this multiplexer, which is controlled by T2. Yeah, so basically we add multiplexers to break the circuit, to partition the circuit. And with this multiplexer, we can apply input directly to the subcircuit and observe some output directly. That's one ad hoc technique. Another ad hoc technique is to insert some test points to enhance the controllability and observability. Say we can insert, for example, insert control point here. Say this is an NOR gate. Normally, this control point will have voltage level of low, so it just pass the other inputs to the output. But when this control point is raised to high, then the output of this NOR gate will be 0. So we can control this directly through a primary input. This is a pin that connects to the external side of the IC. So this is to improve the controllability. This is another control point. So okay, if you have an AND gate, then you can use 0 input to control it. And this is an observation point. So we add a wire here and connect directly as an output pin, so we can observe it directly. Or we can add some multiplexer here, so we can control the input to this part of a circuit directly through the multiplexer. So these are some ad hoc techniques you can think about. Here are some guidelines for ad hoc DFT, design for testability techniques. So we should design circuits to be easily initializable. So when you turn on the power, you should initialize those storage elements, either to 0 or 1. Provide logic to break global feedback paths. You can have some means to break the global feedback, and to keep analog digital parts physically apart. If you have a mixed signal design that contains both analog and digital circuits, you should separate them in different locations. And you should consider the tester requirements. You have an IC tester, there is a limitation on the number of pins available. You should consider this, etc. These are ad hoc techniques. The other type of DFT is more systematic. It can be named as scan path techniques. So say, consider we have a sequential circuit like this. It has storage elements here to store the states and some combinational logics. And we have a clock to the state. And we have some primary inputs and primary outputs. And the states are updated in each clock cycle. So this is next state, and this is present state. Now we can add some flip-flops. To make those, say these are internal variables. Internal, you cannot control them or observe them directly. We can add some techniques, circuit techniques to make an internal variable controllable and observable. We should add the following 4 things. First is a test mode pin, second a scan in pin, and a scan out pin. And most importantly, as multiplexer to each flip-flop. Here shows a schematic. Say the flip-flop here, flip-flop here, the flip-flop part, the storage part of the sequential circuit is here. Now we modify each flip-flop by adding a multiplexer at its input. So basically, it's like this. We have a, say here, we have a eta flip-flop. The input, this is clock. Clock signal is output. At each input, we add a multiplexer. Now this multiplexer is controlled by the test mode control. Normally this is 0, so the D flip-flop receives normal input from this pass. But in the test mode, this goes too high, and we make the following connection. We say so. We have a scan in. This is primary input. Scan in goes to this flip-flop, and the output of this flip-flop goes to the input of the second flip-flop, and the output of second flip-flop goes in to the input of the next flip-flop, like a chain. It's for scan pass. But in the test mode, the flip-flop is connected like this. Input goes from here to the first flip-flop, and output goes to first flip-flop goes to the input of second flip-flop, and this goes to the third one. If we have more, it continues like this, and finally, this goes to a primary output. And this is called a scan structure. A signal will go through all the flip-flops. So by doing this, you can control the input of each flip-flop. So the input can go into each positions after certain clock cycles. And so here, say, you can control the signal here. And these signals are the input to the combinational logic. You see, these signals are the input to the combinational logic. So, but this, you can control the input of the circuit. You increase controllability. That's the first part of the first one side of the technique. The other side of the technique is that you can observe the output. Say here, the output of a combination is here. After one, say when you set it to normal operation, this output will propagate to the propagate through the flip-flop. It propagates through the flip-flop. Then you turn the circuit into a test mode again. Then these outputs can be observed through this scan path. So that's the basic concept. So each flip-flop layer, we turn it into a scan flip-flop. Basic scan flip-flop is a normal flip-flop with a multiplexer input. But in the test mode, all these scan flip-flop are connected in series, in serial connection. Now, for the test pattern generation, we use combinational test pattern generation, like using D algorithm to obtain test vectors for all test files in the combinational circuits. And for shift register, these things are called shift register in the test mode. So we add a shift register test and convert ATPG test into scan sequence. Here are some design guidelines for the scan path DFT techniques. We should use only clocked D type of flip-flops for all to store all the state variables. And we should have at least one primary input pin for test. Basically, we have a scan in, this test input. And all clocks must be controlled from primary inputs. The clock signal of the flip-flop, the clock signal of the flip-flop. So not go through any combination logic. So come directly from the primary input. And clocks must not feed data inputs of the flip-flop. A clock signal should only go into the clock input of the flip-flop. It should not go through some combination, then go into the data input of the flip-flop. And the scan test procedure is like this. Basically, there are 4 steps. The step 1 is to test the shift register, to test the flip-flop. By shifting in the sequence, this sequence 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, etc. From scan in. The purpose of using this is that this sequence contains all the transitions. It has 0 to 0 transition, 0 to 1 transition, 1 to 1 transition, 1 to 0 transition. All the possible transitions are contained in this pattern. So you should be in this pattern and observe it at the scan output. If you observe the same output, then the shift register is okay. So the flip-flops are okay. When flip-flops are okay, then you can move into the test of the combinational logic. Step 2 is to load the pattern. Say you have a first test pattern for the combination logic, and you wanted to test a fault in a certain point. So you shift in, or scan in the first pattern. So the scan pattern will goes in through this shift register. So the data are available at these points. They serve as input of the combination logic. So we load the pattern input to the combination logic. And so step 3 is to return to normal mode, not test mode. So normal mode. So the combinational circuit will respond to its input, and the output of combinational logic we'll go to the output of these flip-flops as normal operation. Then after step 3, the output are actually are stored at the output of the flip-flops. Now we wanted to observe it. So step 4 is to switch back to the test mode. So we can shift these flip-flops output to the scan output. We shift them out. Let's shift register. We shift them out to the primary output, to the scan output, to observe it. At the same time, you can fit in. So at the same time of scanning, you can fit in the test vector for the next test. Next test is another point, another file for another file in the combinational circuit. So when you are scanning out, at the same time you can shift in the test vectors for the next test. And with this 4 step, you complete one test, and you repeat this for other tests. Because for combinational logic, they are you could test it in many ways. So you can through this scan path, we can control the inputs to the combinational logics, and we can increase the observability of the combinational logics. Okay, so that's the most important DFT techniques. Use scan paths. Another scan technique, scan DFT technique, is random access scan. Actually, for the scan test, this scan in, scan out operation is something similar to the configuration in FPGA, or in the so-called programming of FPGA. You also have this kind of series shift register to write data in. But here we write data in and we observe data from the data from coming from the internal nodes. So this is a serial operation, and it takes quite a number of clock cycles to shift in the data or to shift out the data. A random access is a method to increase the speed of the test. The idea is like this. The idea is to address those flip-flop. Here is latch directly. Say we have some memory decoder here. At that time, one of these memory decoder output is high. I say I want to address to this latch. So at a certain time, this signal is high. Then the scan in signal, well, actually scan in signal goes into the input of all the latches. I see scan in goes to the input of this directly without series connection to here to here. So the scan in data is directly available at each latch. Then when this say this latch is selected by the address decoder, its output can be passed to the scan out directly, so you can observe that. This is like a random access memory. You can adjust to individual latches directly. So this provides the ability to watch a node in normal operation mode. The disadvantage is that the hardware cost is large. We need a memory decoder. And we need more pins. So any questions regarding this scanning technique? No. Let's continue on this random access scan. So random access scan is also a scanning technique, although it does not contain a scan path, a serial register, shift register. But it falls into the principle of a scan design. And so it's still a scan design. And the latch, all the latches here in the scheme are short circuit. These latch outputs are short circuit. This is called a wire end. Normally, the output of the two nodes, two logic blocks should not be short circuit. You know, if one output is 1, the other output is 0, you connect 1 to 0 together, you generate a direct current path from VDD to ground. And normally, this is prohibited. But in order to save the pin, we short circuit the output because we have a memory decoder here. At that time, only one of the latch will be active. The others will not be selected. So this wired end is okay. And it serves the purpose of reducing the output pin. Without this short end, you need an output for each latch. That's very costly. So the key element in a random access scan DFT technique is a addressable latch. There are many circuit design for such a addressable latch. Here shows an example. This is the core of the latch. A latch contains a positive feedback gate. In normal operation, it has a there are 4 modes of operation. So basically, it's one normal operation is just a normal latch. The second mode is that you can clear the output. There is a signal, input signal, common clear, that you can reset the output to low. So you have the control. Another mode is to preset. You can set the Q to high, output Q, through this pin. So basically, this is just a flip-flop or latch that can be cleared or set. But in addition to these normal functions, a scan mode is added. In the scan mode, this is select. Basically, this is the address to this latch. When this mode is high, then the output Q is passed or propagated with inversion to the scan output. Normally, if this is not selected, then this is low, 0. 0 input to a NAND gate has a fixed output. But when this is 1, then it just pass the other input to the output with inversion. and the scan output is a wide end, so that you can observe the output from the scan output pin directly. Okay, so that's about the DFT techniques. Now let's take a 3 minutes break before going to chip debugging tools. Okay, let's continue. Well, sometimes so after the test, you may find that a circuit is not functioning properly. You want to find out the root of the problem, not only the logic source, but the root of problem. And there are some tools to debugging for debugging a chip. The most obvious one technique is to look at the chip. Our chip is, I mean, the resolution is very fine, so we should use some microscope, or sometimes use the scanning electron microscope to observe it directly. Or we can use the electron beam to observe the imaging of a chip and to control it. So in this technique, the machine shoot electrons at the chip and measure reflect electrons. With this, patterns can be observed in a very fine scale. So basically, ground metal looks bright and high voltage metals look dark. So you can even observe it while the chip is working. or use the third tool is to use laser voltage probe. So we have a picosecond, very short pulse, laser aimed at silicon, and measure reflectance. And reflectance depends on carrier density. Through this, you can observe whether a transistor is conducting or not. Now, the next method tool is through the time-resolved emission. We detect photons, light emitted by switching transistors, because carriers in the transistor channel has a temperature, and everything that has a temperature emits some light, emits infrared light. In this case, it's near infrared light. And this emitted light, this IR light is transparent. Silicon is transparent to this infrared light. So we can observe this temperature in this method. And this is non-invasive. I just observe it without injecting anything. And the last and very powerful method is called focused ion beam, FIB. This is powerful because it allows post-fabrication editing of the circuit. You can change the circuit after the fabrication. Here shows some, these are some pictures showing some defects. So these are pictures taken by scanning electron microscope. So by looking at the chip, say, using this tool, you can find some origin of the circuit spark. For example, an exposed photoresist, or some alien particle, or maybe some dust fall into the chip during the manufacturing process, some scratch. This direct observation is useful. So that's to find the source of problem. And there is a way, as I said earlier, focused ion beam allows post-fabrication edits on silicon. You can fix a chip problem before making another round of fabrication. So basically, this method, FIB, is used to check if a fix to a bug will actually work or not before you burn the money for a new design. It is very expensive. The service is charged hourly. So don't do it unless you need to. Usually it takes 3 to 4 hours to fix a single problem. Only one fix, it only fixes one chip at a time. It's not for mass production, it's for individual chip. You can edit individually. And FIB edits can be additive or subtractive. Additive means you can add some layer. Subtractive means you can remove some layer or cut some wire. Basically, you can cut wires or lay down new wires. In the past, FIB used to be from the top of the chip. You can do this editing from the top. But today, it can also be used from the back side, from the substrate side. And this is useful for flip chip packaged die. This shows a simple schematic of the FIB technique. Basically, the machine shoot some ion beam focused at a certain point on the chip. So this is a chip. This ion is usually gallium ions. So it can cut a wire through the sputtering effect. Focus on you inject a large current of gallium ions. You may cut a line, or you can do deposition through this process, which means you can deposit a metal layer. Now here shows some shows an FRB example in the process. So these are metal wires. Then I want in this process some metal deep below this layer needs to be added. So here the first step is to define windows for cuts. So these two locations needs to be cut. Then through the FRB, we can open the cut window and cut it through. So this is a zoom-in view. You see the FRB is basically a micro machining technique with very fine resolution. So the metals are mute. Then through the same technique, we can depose the metals, metal to make connections. Okay, so you see the FRB can perform post fabrication editing of metal layers. So can remove wires and add new wires, but FRB cannot add new devices, new transistors. So the designer often throw in a little of extra layout for the transistors, just in case. Just in case you can connect those transistors back into the circuit. But you need to put them in schematics as well in order to pass the layout versus schematic checking. So you put some spare gates, and some basic cells with grounded input. Normally they are not used, but just in case you can use the FRB to connect these spare gates into the circuit with the purpose of fixing certain bug. The basic gates you put in usually contains a mixture of inverter, NAND gate, NOR gate, a few flip-flops. So if you have empty space available in the design phase, then you may plan on inserting this in your block. Some people call these spare gates as happy gates for reasons obvious to the debugging team. Okay, so that's about the testing. Any questions on this regard? If no, let me quickly go through the course. Okay, so here is a wrap up of the course. There are 6 parts. First part is technology chains. In this part, we learned the high-C technology chains in transistor count, etc. And we learned the CMOS fabrication process, the photolithography technique. And for nanometer photolithography, there are challenges and solutions. The challenge is resolution challenge due to the diffraction limit. We know that there is a deep UV technique which can be used down to 7 nanometers through a number of resolution enhancement techniques, and extremely ultraviolet UV techniques for 5 nanometer and beyond. And the structure of a transistor in nanometer regime, basically FinFET. FinFET is used at 22 nanometer and below. That's a chart. Can I see it in Zoom? Can you see it in Zoom? I think I have already shared it. Okay, anyway. You see, nothing showing on the screen. Let me stop share and do it again. Can you see it now? Screen sharing is paused. Stop share, I'll do it again. I think you can see it now, right? Nothing? Can some of you try to hear? It's okay now, okay. Thank you. So that's part 1. Part 2 is about implementation methods for modern digital IC, digital circuits. We have these implementation methods: system on chip, ASIC, FPGA, dedicated processor, general purpose processor. Our focus is on FPGA and ASIC. FPGA contains configurable logic block. We have lookup table flip-flops there. And the interconnect is configurable. And the method to configure it is to use SRAM. That's a mainstream technique. And there are also other resources in the FPGA, including DSP memory, phase lock, I/O, etc. ASIC, we have stainless cells there. So that's the second part. Part 3 of the course is about the design flow. We learned the Y chart in this part. There are 3 design domains and different abstraction levels. We have this structural design domain, behavioral design domain, and physical design domain, or geometry domain. In the simulation, we have different circuit models and signal strings. Circuit models at system level, register transfer level, gate level, switch level, device level. For signal strings in logic simulation, we have strong, weak, and high impedance. In the ASIC design flow, there are many 2 steps: synthesis and place and routing. Synthesis is from behavioral description into net list. Place and routing is from net list to layout. These processes are now automatic. They are done by software. And FPGA, similar, we have 2 steps. There's a synthesis place and route are provided by the software that you are using. That's part 3. So these 3 parts are before the midterm test. And after midterm, we have this hardware discrete language, Verilog. In Verilog, there are structural description, declarative description, also known as data flow description. The keyword for this declarative description is assign. And we have a procedural description, also known as behavioral description. We use always block to show procedures there, procedural behavior there. And the key thing we learn here include a blocking assignment and non-blocking assignment. You should be able to know the difference. Delay controls in Verilog, and use Verilog to implement finite state machines, as you have done in your 3rd homework. Part 5, we spend a lot of time in part 5 as data path. We began with the timing associated with flip-flops. There are setup time, hold time, clock to queue delay. There is a question in homework 4. You should be able to solve it. Adders, the most basic form is a ripple carrier adder. Then we spend a lot of time to learn fast adder techniques. The fast adder we learn include carrier bypass adder, or also known as carrier skip adder. Carrier select adder. There are 2 variations: linear type and square root type. Carrier look ahead adder. And we have different carrier look ahead trees in the implementation. Apart from these binary adders, we also learn adders based on residue number system, adders based on redundant number system. Those adders do not have the problem of carrier propagation. And pipeline method can be used to implement adders to increase the throughput, multipliers, array multiplier, and distribute arithmetic for inner product. This distribute arithmetic is important. And then we learn the simple processor, which include all the necessary functions of a processor. And finally, is the testing. We just learned. We learned the stuck at fault model and the ATPG algorithms and design for testability techniques. So that's a review of the course, a brief review. Oh, okay. Here is the